In the previous lecture, we talked about Slater determinant. In this lecture, we are going to look at the energies of this determinant. So as a simple example, we will consider helium atom again. Let's consider a two-state model. So we only consider one s orbital and two s orbital. So of course, we know the ground state of helium atom is 1s2 configuration. This is the 1s2 configuration. And of course, this gives you a singlet. Another configuration could be 1 up and 1 down. But of course, we know this is not a spin eigenfunction. And the singlet is actually a linear combination of 1 up, 1 down, and 1 down, 1 up. So this is the configuration 1s1, 2s1. And this is the singlet. So let me put 1 here. You can also have another state. This is the 2s2 state. So these three configurations give you singlets. You can also have triplets. You have 1s1, 2s1. This is, of course, a triplet state. So I put a 3 here. Now, of course, this means that I have 2 alpha electrons. So I can use 1s alpha, 2s alpha to denote this particular electron configuration. You can also consider 1 up, 1 down, plus 1 down, 1 up, right? So this is 1s1 to s1, and this gives you triplet. Of course, we can have 2 beta electrons, right? So 1s beta, 2s beta. This is also a triplet. Now, we have all of these possible configurations. The question that we want to ask is, what is the order of the energies for these determinants? All right. So let's first look at the 1s2 configuration. This is the ground state configuration. Let's start from here. In the previous lecture, actually, we have already performed a variational calculation on the ground state helium atom. But in that lecture, we didn't really consider the electron spin. Here, I want to show you that the ground state energy for helium atom does not include contributions from the spin degrees freedom. So let's consider 1s2, H, 1s2. So here, this H is the exact Hamiltonian. So we do not consider spin-orbit coupling in the Hamiltonian. Usually, for light atoms, those terms can be ignored. So in H, you do not have an explicit term that depends on spin. So we call this is a spinless Hamiltonian. Okay, so this is enough for our purpose in this lecture. So what is 1s2? Well, of course, 1s2 is given by a Slater determinant. This is 1s1, alpha 1, 1s2, beta 2, minus 1s2, alpha 2, 1s1, beta 1, H, 1s1, alpha 1, 1s2, beta 2, minus 1s2, alpha 2, 1s1, beta 1, right? And divided by 2, of course. For each Slater determinant, you have a normalization constant, 1 over square root 2, right? So for this bracket, you have 1 over 2 in front of this expectation value. Okay. Now, this is, of course, equal to 1 over 2, 1s1, 1s2, alpha 1, beta 2, minus alpha 2, beta 1, right? So you can group the spin function together and the spatial function together, right? H, 1s1, 1s2, alpha 1, beta 2, minus alpha 2, beta 1. So you see, when you do this product, you will have alpha 1, beta 2 interact with alpha 1, beta 2, right? Because this H does not depend on spin. Therefore, you simply have an inner product of alpha 1, beta 2 and alpha 1, beta 2. And that, of course, give you 1, right? And you have another term, minus alpha 2 beta 1 times minus alpha 2 beta 1, which again give you positive 1, right? This is the normalization condition for the spin function. And therefore, this expression can be further simplified to 1 over 2, 1s1, 1s2, H, 1s1, 1s2, times 1 plus 1, right? The first one comes from alpha 1, beta 2, the inner product. And the next positive one comes from negative alpha 2, beta 1 times negative alpha 2, beta 1, right? All right. So in the end, what you have is essentially just this term, right? You only need to care about the expectation value computed by using the spatial octal, right? That is why the energy of the ground state helium doesn't include contribution from spin. Okay. Now, let's expand this term. So you have 1s1, 1s2. H is, of course, let's use atomic unit. So it's 1 over 2 gradient squared for the first electron, minus 1 over 2 gradient squared for the second electron, minus 2 over R1 minus 2 over R2, right? 2 is the nuclear charge for helium atom, plus 1 over R12. This is the electron-electron repulsion. 1s1, 1s2. Okay. Now, this term can be separated to 3 terms. Or you can say this term can be grouped to 3 terms. The first term is only about 1s1, because you see, this operator and this operator only cares about the position of the first electron. And this operator only care about the position of the second electron. It is the 1 over R12 connect the both electron, right? Okay. So the first term is 1s1, negative 1 over 2 Laplacian for the first electron minus 2 over R1, 1s1, and 1s2 simply becomes an inner product, right? Okay. And of course, we know this inner product is equal to 1. The second term, similarly, it's 1s2, 1 over 2 Laplacian for the second electron minus 2 over R2, 1s2, times the inner product of the first electron. Again, this term, of course, is equal to 1. Now, the third term, of course, you cannot separate 1s1 and 1s2, because now this first electron and second electron are connected by 1 over R12. Right? This is the distance between the first electron and second electron. This is not a separate term. This is not a separable term. You have to evaluate this 2 electron integral. And actually, in the previous lecture, we talked about how to evaluate this integral, right? You need to take advantage the properties of the R12 function, right? You need to expand it using spherical harmonics. And then you need to do the calculation. You need to evaluate the integral in the spherical coordinate. Okay. So the first term, let's see, what is this first term? This first term is exactly equal to the 1s orbital energy for a hydrogenic atom with the nuclear charge being equal to 2, right? So this can be written as epsilon 1s or E1s. So this is the 1s orbital energy for a hydrogenic with the nuclear charge 2. What is this term? This term is exactly the same as the first term, right? What you do here is you simply use 2 as your label, right? This is your label for the electron, but this 2 here is a dummy index because you are integrating over this electron coordinate. So this integral gives you exactly the same value as this first integral. So again, you have epsilon 1s, another 1s orbital energy, right? Because you have 2 electrons occupy the same spatial orbital, right? In this lecture, we only consider restricted determinants, okay? All right. And the third term, of course, This is the integral that you must evaluate. And we denote this integral as J, 1s, 2s. This J, of course, is the so-called Coulomb integral. Or you can say it's Coulomb repulsion, right? If you want to write down explicitly the integral, that means you really have a double integral. The first integral is integrating over the first electron. The second integral is integrating over the second electron. And because you have 1s, this is 1s complex conjugate times 1s. And this gives you the density, the probability density of the 1s electron, right? So this is the probability density of the 1s electron. And the variable, of course, here is R1. Similarly, 1s2 complex conjugate times 1s2 give you the 1s probability distribution again, but here you're considering the second electron. Then divide by R12. dr1, this is for the first integral, and dr2, this is for the second integral. So you see, this is actually the classical expression when you have two distributions of the electrons. Classically, if you want to evaluate the repulsion between two clouds of electrons, this is exactly the expression you use. So Coulomb integral can be viewed as kind of classical expression, okay? But of course, this comes from the quantum mechanical evaluation of the expectation value, okay? But of course, you can view it as you're calculating, classically, you're calculating the repulsion between two clouds of electrons, okay? And of course, in the end of the day, you see this energy expression for the ground state helium atom doesn't include contribution from spin. Okay. And of course, in this lecture, we haven't considered the variational optimization of the wave function, right? So if you just evaluate the value of epsilon 1s and J1s, 2s using the nuclear charge 2, you will not get a very good energy. But qualitatively, it's fine. Quantitatively, you have to consider variational optimization of the wave function. So here I should say, note, we haven't considered variational optimization of the wave function. Okay. Actually, in the next lecture, we will talk about how to do this variational calculation for a multi-electron system systematically. But in this lecture, we just focus on the energy of the determinant. This is actually the prerequisite for understanding what we're going to talk about in the next lecture. Okay, now this is the ground state. Next, let's look at a very simple triplet. So let's consider this configuration. You have 1s alpha and 2s alpha. Okay, this is of course a triplet. 1s alpha, 2s alpha. So the ground state, of course, is a singlet. Now let's consider the triplet. So you have this triplet, 1s1, 2s1, H, 1s1, 2s1, triplet. Okay. Again, you can write down the Slater determinant. 1s1 alpha 1, 2s2 alpha 2, minus 1s2 alpha 2, 2s1 alpha 1, h 1s1 alpha 1, 2s2 alpha 2, minus 1s2 alpha 2, 2s1 alpha 1 divided by 2. Again, this 1 over 2 factor comes from the product of the normalization constant. Okay. And in this case, you can actually rewrite this expression by separating the spatial part and the spin part. So for the spatial part, you have 1s1 2s2 minus 1s2 2s1. For the spin part, we have alpha 1 alpha 2. H 1s1 2s2 minus 1s2 2s1 alpha 1 alpha 2. Okay. Don't forget about 1/2. Okay, you have 1 over 2, this factor in front of this expectation value. Okay. Now, you see, you have alpha 1, alpha 2, alpha 1, alpha 2. Of course, this inner product is equal to 1, right? And therefore, this expression can be simplified to 1s1 2s2 minus 1s2 2s1 h 1s1 2s2 minus 1s2 2s1. And again, we already know the expression for h. You can separate this expectation value into multiple terms, right? So if we consider, for instance, the first term would be, we have 1 over 2. We always have 1 over 2. Let's consider 1s1. So let's consider the operator for the first electron only. So you will have 1s1 negative 1 over 2 Laplacian minus 2 over R1, 1s1, right? You will also have another term, 1s2 negative 1 over 2 Laplacian for the second electron, 1s2. Okay, this is the first term. The second term, again, you have 1 over 2 in front of this expectation value. So you will have 2s1 negative 1 over 2 for the first electron, 2s1 plus 2s2 for the second electron. Right? And you will have non-separable term because now the terms left they are all connected by the 1 over R12 operator. So these terms are not separable. So you will have 1 over 2, 1s1, 2s2, 1 over R12, 1s1, 2s2, plus 1s2, 2s1, 1 over R12, 1s2, 2s1. And you will have another two terms. Here you will have negative sign, right? Because, well, you see, when you do this product, you will have in total 8 terms, right? So you will have, you see, this is the positive sign times a negative sign term, right? and a negative sign term times a positive sign term, right? So you will have 1s1, 2s2, 1 over R12 times 1s2, 2s1, right? Plus 1s2, 2s1, 1 over R12, 1s1, 2s2. Right, so in total we have 8 terms. All right, so again, let's look at those terms. So let's look at the first row. Let's see. This expectation value is, of course, equal to this expectation value, right? Those two are equal. Why is that? Because the only difference is the dummy index, right? This is the dummy index. The value of the integrals are exactly the same. All right. Now let's look at the second row. Again, the difference between these two terms is the dummy index. You simply replace 2 with 1, or you replace 1 with 2, right? So they are exactly the same. Now let's look at the third row. This term and this term, again, they are exactly the same. Why is that? Because here the dummy index is 1, 2. Here the dummy index is 2, 1, right? You simply exchange label 1, 2 and 2, 1, right? And this is, of course, the bra. In the cat, you have 1, 2. And here in the cat, you have 2, 1. Again, you exchange the label, right? Now, for the last row, this integral, of course, again, is equal to this integral. You have 1, 2 here, but you have 2, 1 here. You have 2, 1 here, and you have 1, 2 here. So it's nothing but exchange of the label. All right. So this first term this is, of course, the 1s orbital energy. This is, again, the 1s orbital energy. So you have 2 times the 1s orbital energy. And divided by 2, you get 1s orbital energy, right? For the second term, not the second term, the second row, you have, this is the 2s orbital energy. This is also the 2s orbital energy. And of course, divide by 2, you get 1 2s orbital energy. All right. Now, what is this? This is, of course, the Coulomb repulsion, right? Because you have 1s star times 1s for the first electron, and 2s star times 2s for the second electron. Here, it's the same. It's the 1s star times 1s for the second electron, and 2s star times 2s for the first electron. So you have 2 times the Coulomb repulsion. And therefore, you divide by 2, you have 1 Coulomb repulsion between the 1s orbital electron and the 2s orbital electron, right? Now, let's look at the cross term here, the last row. For the last row, this is something interesting. You see, here you have 1s star for the first electron, but in the cat, you have 1s for the second electron. You exchange the label between 1 and 2 within a single bracket, right? So here, again, in the cat, you have 2s star for the second electron, but in the bra, you have what? sorry, this is the bra, and this is the cat. In the bra, you have 2s star for the second electron, and in the cat, you have 2s for the first electron. Again, you exchange the label between 1 and 2. If you do not exchange label, then what you have is the Coulomb integral. But here you exchange the label, right, within a single bracket. So we call this integral as the exchange integral. And obviously you have 1 exchange and 2 exchange, and they are identical. And therefore you have -1 exchange integral between, between 1 mass, 2s electron, right? Okay. So here, this is something that I like to talk about. The first thing here, we noted that the difference between this configuration, this triplet 1s alpha, 2s alpha, and the ground state 1s2 configuration is that now this term actually comes from the spin. Okay? I will talk about this later in this lecture, but here you need to have a concept that this term, why do you have this exchange? That is because you have a pair of spin parallel electrons, and then you can have this exchange. In the first case here, we don't have exchange, right? You don't have 1s2 and 2s1 within the same bracket, right? So what you have here is simply a Coulomb exchange, a Coulomb integral. Here you have 1s1, here you still have 1s1. Here you have 1s2, and this is 1s2. So you didn't exchange the label of the electrons. So this is a Coulomb interaction. On the other hand, for a pair of spin parallel electron, you have an exchange interaction. This is something very special. So if we look at so you have one mass electron, say the distribution of one electron is something like this, right? It's a spherical distribution. Okay. And of course, you can have a 2s electron shell. This is the 2s electron. Again, this is spherical, right? Okay. So the interaction between these two electron clouds give you what? If you consider the classical interaction, then you have the electrostatic repulsion, and that is J1 mass 2s, right? This is the repulsion between the 1 mass electron distribution and the 2s electron distribution, divided by R12, dr1, dr2, right? This can be viewed as the classical electrostatic repulsion. So in classical mechanics, this is the only term that you will get, right? When you consider the interaction between two distributions of electrons, this integral, this J integral is the only integral that you will evaluate. This is what you have in classical electrostatics, right? However, when you consider a pair of spin parallel electrons, 1s alpha, 2s alpha, there is an additional term that's not there in classical mechanics. You have K1s, 2s. You have this integral, which is what? Based on the definition, right? We have the Dirac notation. This is 1s star 1, 2s star 2 times 1s. Now you put 2 here. 2s, now you put 1 here. You exchange the label, okay? So the label in bra is 1, 2. But the label in the cat is now 2, 1, and therefore this is called the exchange integral over R12, right? Again, because the way to relate the first electron and the second electron is through this 1 over R12 electron repulsion operator, dr1, dr2. This is something unique in quantum mechanics. So this is purely quantum mechanical. Right? This is a purely quantum mechanical interaction. Okay? This interaction is called exchange interaction. Or this integral is called the exchange integral. Okay? Now, we can rewrite K as 1 as 2s to a form that is something similar to the Coulomb repulsion. So if we write 1s star 1, 2s star 2, and here if we write 1s1, 2s2, then of course this becomes the Coulomb integral, right? But for Coulomb integral, if you only consider the classical Coulomb integral, what you have in between is simply 1, or you can say the identical operator, right? But here, because you have exchange, what you have is the exchange operator, P12. So here, P12 is called the exchange operator for the first electron and the second electron. What it does is that if you apply P12 on a function, R1, R2, then it simply gives you this function R2, R1. So this operator switched the position or switch the label of the first electron and second electron. So this is the exchange operator, okay? So if you write the exchange integral in this way by using the exchange operator, then you can combine the Coulomb interaction and exchange interaction together. That is to say, we can combine the last two terms together. So now you see you will have, so the last term, Js 1s, 2s minus k 1s, 2s can be combined together into one expression. And this is simply 1s star 1, 2s star 2, the identical operator, or simply you can write it as 1, minus the exchange operator, 1s1, 2s2, over R12. Okay? So this is something unique in quantum mechanics. Without considering the exchange operator, then of course K becomes J. But for a pair of spin parallel electrons, 1s alpha, 2s alpha, you have this exchange operator in between. This is something intrinsically quantum mechanical. You have no classical picture. Okay? So I should put a remark here. For spin parallel electrons, we have this exchange integral between these two alpha electron or between these two beta electron. And this integral, of course, is bigger than 0, okay? And the total energy of this determinant for a particular electronic configuration is lowered by negative k alpha alpha or negative k beta beta. This is very important. This exchange interaction between two spin parallel electrons lower the system energy. Okay? A pair of spin anti-parallel in a single determinant do not have exchange interaction. Okay. So even if you consider, let's consider if you consider a single determinant, one up and one down, there is no interaction, there's no exchange interaction between these two electrons. Of course, you can have J, A, B, right? A and B are the label for the spatial octal. You can have J, A, B, but you do not have K, A, B. You don't have exchange integral. This is because when you write down this determinant and you evaluate the expectation value, you will have, for the spin part, you separate the spatial part and the spin part, right? And then you will have alpha I, beta I. You will have this term. This term will give you 0 because for the same electron, alpha and beta are orthogonal. And this is the reason that you have no exchange term. This is exactly the reason. Okay. Another thing that I want to emphasize here, I write down in a single determinant. If you consider a linear combination of determinants, because the interaction between two determinants, you can have, it's possible that to have exchange interactions. Again, just like the example I just talked about here, one up, one down. If you only look at one up, one down, or if you only look at one down, one up, you don't have an exchange interaction. However, this is not a spin eigenfunction. This is not a spin eigenfunction. If you do a linear combination of these two, you will have spin eigenfunction. And when you evaluate the expectation value based on the spin eigenfunction, in the integral, you will have the interaction between these two determinants. And that will give you exchange interaction. Okay? And this is something special. If you consider this, well, it also depends on whether or not you use SDA minus SDB, or you consider SDA plus SDB. You will have different results. Okay, we will talk about this later, but here the point is that I want to emphasize that this conclusion about the exchange is for a single determinant. Okay, the Coulomb repulsion is always there, that's for sure, because you can have classical analog. Okay, you always have classical Coulomb repulsion. That is, you always have J integral. J integral is larger than 0, and because classical repulsion, or quantum mechanically, because of the J integral, the system energy is actually raised by J. All right. But for the exchange, If you only consider a single determinant, then a pair of spin anti-pair electrons do not have exchange interaction. Okay. Now, the next thing that we need to understand is, okay, now you have singlet, right? Let's go back to the beginning. We talk about the singlet, right? This is the ground state singlet. We talk about a very simple triplet. You wonder, what's the energy difference between these two? Is the singlet 1s2 always the ground state? Is the triplet always higher in energy than singlet? Is it true? This is a very important question about the singlet-triplet gap. This is actually very important in understanding chemical reactivity, in understanding molecular structure. In the next session, we will talk about the singlet-triplet gap.